Okay, so I'm going to tell you something today about rules-based AI. As we're already probably a bit behind schedule, I'll skip on and go to the agenda. So yes, I'm going to tell you what rules-based AI is and why I think you need it. I'll say a little bit about how we've developed research that we did at Oxford into a sort of viable system that can be used in real applications, and I'll illustrate that with a few use cases, particularly selected from the financial services sector. A little bit of background about me. I'm a professor at the University of Oxford. I've been working in this area for a long time. I was involved in standardization activities around the semantic web, and I've written a lot of papers, and I'm a co-founder of Oxford Semantic Technologies, which is a university spin-out commercializing technology in this area, and actually was recently acquired by Samsung. So we're now actually part of Samsung Electronics. And what gets me out of bed in the morning is this idea to turn the many decades of academic research into a reality that's actually used in real applications. Okay, so quickly, what's rules-based AI? Well, probably most of you have heard of knowledge graphs, which in many cases actually are really just data graphs. So it's a graphical data model as opposed to a sort of tabular data model in more traditional databases. And the graph links together various pieces of information, talking about, for example, customers, institutions, trades, whatever it might be. So this is the knowledge or the data graph, but to turn that into real artificial intelligence, you need to layer on the top of it some expert knowledge and reasoning capabilities. And I'll illustrate that with a very, very simplified example. So this might be what our knowledge graph looks like. So this talks about, for example, banks and insurance companies. We have just in this very simple example, we have just one bank, which is BNP, and one insurance company, Aviva, and it tells us about things like their assets, the location of their headquarters, and so on. So this is already useful, like as a regular database, we can answer simple questions such as what is the asset value of BNP? And in knowledge graphs, the way we answer this kind of question is we just do a simple graph matching operation. So our query actually just looks like a graph pattern that has some variables, blank nodes, whatever we like to call these, in it. We match that into our graph, and wherever these variables match in the graph, this is what we return the answer value, which in this case is 2,867 billion being the asset value of BNP. Okay, but what if we want to answer a more complex question, such as which are the financial institutions that are headquartered in the European Union? So it kind of looks like there should be enough information in our graph to answer this kind of question. For example, we know that BNP is a bank, and a bank's a kind of financial institution, and its headquarters is in Paris, which we know is the capital of France, and France is a member of the EU. So we sort of expect Paris to be in the answer, but for a computer to actually return that answer is not so simple. For instance, we need to know what this kind of edge really means. And in particular, we need to know that intuitively, if X is a type of Y and Y is a kind of Z, then X is a type of type Z. And in particular, in this instance, we need to know that this kind of relationship means that both BNP and Aviva are financial institutions. And we need to represent this expert knowledge explicitly in the system, which we do by way of a rule. Similarly, we need to know about the relationship between HQ location and the country in which the institution is located. And again, we can add a rule that tells us that because if institutions are located in a city and that city is the capital of a country, then they're located in the country. And finally, we need another rule to tell us about the relationship between countries and unions like the European Union that they're a member of. And if we add all this expert knowledge, basically what we do is we augment the graph with these additional inferred edges that are the result of adding expert knowledge to the data that we have in the graph. And now we're able to answer this question, and the answer comes out to be BNP and Aviva. Well, hopefully some of you are actually paying enough attention to realize that there's a problem here, which is that our original data was out of date, and actually the UK is no longer a member of the European Union. So things change in the world, our data gets updated, and we need to delete this edge. If we're using reasoning to actually augment the graph with additional edges, then we need actually to do something a bit smarter, which is that we need some sort of truth maintenance, because when we delete this edge, actually we need to delete this derived edge as well, because now the UK no longer matches this rule, which tells us about the relationship between countries and unions that they're a member of. So we lose Aviva from the answer. And I'll come back to this later. It's an important point in applications. So many of you may be thinking, well, isn't this all kind of old stuff? In the modern world, we just use machine learning or large language models or something like that to do all of this kind of stuff auto-magically. Well, actually, although machine learning and language models have many very useful features, they also have some weaknesses, and similarly, rules-based AI has strengths and weaknesses, and we need to think about what kind of application we have in order to determine what kind of AI is appropriate. So in particular, we know that machine learning works with large-scale data. It's good at answering relatively simple questions and overcoming problems like noisy data. And the results it produces are not necessarily correct, but they're statistically likely. On the other side, rules-based AI works with large-scale data and this additional expert knowledge. It's able to answer complex questions using a combination of the data and expert knowledge, and the answers it produces are precise and accurate. And if we think about the kinds of scenario where we might want to use these different kinds of AI and their strengths and weaknesses, one of the things we might ask ourselves is about information density. And what I mean by information density is the value of each piece of information. And we can see that in the machine learning setting, we have low information density. So actually we could delete quite a large chunk of the data, and that would have little or no impact on the outputs that we get from the machine learning system. In contrast, rules-based AI is typically appropriate in scenarios where we have high information density. So where deleting data from our graph would have a big impact on the outputs. Similarly, in the machine learning setting, typically we have only vague knowledge, so we don't really know what the rules are that underlie the kinds of result that we want to get out of the system, whereas in a rules-based AI system, we have precise knowledge, we know what the rules are. And machine learning systems are usually appropriate in settings where it doesn't matter, or it doesn't matter very much if we get occasional wrong answers, so we can tolerate some errors. In contrast, we might want to use a rules-based AI system in a scenario where errors can't be tolerated, where errors would be costly. Of course, it would be great if we could have the best of both worlds, and this is a very active area of research today where people are trying to combine various sorts of learning and large language models with rules-based AI. And one example is retrieval augmented generation. This is something we're working on at Oxford Semantic Technologies, and you can find an online article about that if you follow this QR code. Okay, so I mentioned that making it real has been an important thing and a motivation for me in my research. We actually developed RDF-Ox, which is the knowledge graph system that we use at Oxford Semantic Technologies. We developed that at the University of Oxford, and we actually spun that out into Oxford Semantic Technologies back in 2016. The idea being to demonstrate that we could use this in real applications and develop this kind of research system into a viable product. So what makes RDF-Ox different? Well, I already showed you about the semantic reasoning, so how it combines expert knowledge with the data in the graph. Actually, most knowledge graph systems don't do that. They don't support this rules-based AI. So really, it's a bit of a misnomer to call them knowledge graph systems. They're really data graph systems. Obviously, if this is going to be viable for real-world applications, we need to be able to scale it up to very large graphs and work at very high speed, which is something that we spent a long time figuring out how to do at Oxford. Another thing is that it's very useful to be able to work across a large number of different kinds of deployment, including things like cloud, all the way down to handheld devices such as mobile phones. And as you can guess, this capability of RDF-Ox is something that was particularly interesting for Samsung. And of course, we have the heritage of Oxford University backing up the technology behind RDF-Ox. So the reasoning functionality it provides is extremely advanced. I already showed you about some simple ways that we can infer things from rules, but these rules can involve quite complicated things like arithmetic and string manipulation, aggregation. Rules can work on absence of knowledge in the graph as well as presence of knowledge in the graph, something that's sometimes called negation as failure. In addition to inferring new facts in the graph, RDF-Ox is also able to explain whenever it derives some new information. And this is very important in many applications. And as I already demonstrated, RDF-Ox does what we call incremental reasoning, which is some kind of truth maintenance. So as the data in the graph changes, it automatically updates the inferred knowledge from the rules in order to be consistent with the new data. Okay, I'm just going to finish by mentioning a few use cases, particularly use cases from the financial services sector. A very interesting one that's deployed in one of our large clients is making autonomous trading decisions. So here, when a trader wants to make a trade, they have to check in real time whether or not that trade is compliant with regulations and with the policy of the company. This is done by using this expert knowledge about regulations and policy, which is captured in rules, and it provides instant feedback to the trader to tell them whether or not the trade is compliant. Several important features here that I mentioned already that RDF supports, and one of these, apart from the speed, because this has to be more or less instantaneous, another really important feature is this explanation that I mentioned. So in case a trade isn't compliant, the system explains to the trader exactly why the trade is not compliant. And it also uses the explanation to suggest some minimal changes to the trade that would make it be compliant. Okay, another application is financial crime detection. In this case, the expert knowledge is used to identify patterns that could indicate dubious transactions or even financial crime. Another application that I wanted to mention, because it actually uses this retrieval augmented generation, RAG, that I was mentioning before. Here, it uses expert knowledge to support customers and, for example, recommend suitable products. And this is combined with the use of large language models to improve the interface, the dialogue interface with the clients. But the rules that actually make recommendations use expert knowledge to make sure that the recommendations are really correct and accurate. Okay, so in conclusion, I just wanted to say rules-based AI, hopefully I've explained roughly what that is. It combines knowledge and data to answer complex questions. It's appropriate in settings where it's important to avoid errors and inconsistencies that, for example, in the financial services sector could be extremely costly. I showed you a number of use cases, including autonomous decision-making, pattern detection, customer services, etc. And I also mentioned our RDFOX system, which embodies decades of research in the area and is already being used by global financial services firms.